to be a part of this course. And now I would request Professor Vineet Sahula. He is professor at MNIT Jaipur, and he is PI for EICT Academy MNIT Jaipur as well. So over to you, sir.
Yeah, thank you, Menka.
Sir, your voice is not audible.
Am I audible? No?
Yes, sir. Now it is audible.
Yeah, thank you. Yeah, thank you, Menka, for working hard to weave the thread of this program right from the beginning. I know it's a very hefty task contacting participants, speakers, arranging logistics, many other things. I think this is quite a relevant program in the today's scenario of India's semiconductor mission, where we are projecting that within 3 years, at least 1 lakh manpower is required for VLSI design. 1 lakh manpower in a context possibly. You all will be the flag bearers of educating the manpower, and all my faculty colleagues here, they will like appreciate that the India semiconductor mission, although it started late, is a right step in a direction of the growth. So very good morning to all of you, my colleagues here, Dr. Menka, Dr. S.J. Nanda, Dr. C. Peryaswamy, Dr. Lintu Rajan, other faculty colleagues in the participants, all students, and staff of my EICT Academy, Ms. Geeta, Mr. Ramesh, Manish, and Deepesh. At the outset, I'm sorry, I would like to thank our director, Professor N.P. Pahadisa, for motivating us and picking and letting us pick some innovative steps to actually contribute overall to the GDP of the country actually. So we are looking forward to actually initiating many efforts. I will just let you know something which is of interest to you in my slide. We are just waiting that Dr. Viren Singh is joining us. Ramesh and Geeta, please see whether he is in attendees. Dr. Viren Singh. We are just waiting for him, just 5 minutes, because he is our esteemed first speaker today, and we'll be continuing with his discourse for next 4 days. We'll take just a, please stand by. We'll wait for him to join.
So by the time Professor Virendra Singh is going to join, may I request Dr. Pariya Sami to say a few words to encourage our participants, please.
Thank you, madam. A very good morning to everyone. First and foremost, we would like to express our sincere gratitude to the Honorable Director of MNT Jaipur and the Chief Investigator and Co-Chief Investigator of ACT Academy, MNT Jaipur, for providing us with this wonderful opportunity. We also extend our thanks to ACT Academy, MNT Jaipur, for considering NIT Calicut as a spoke institute of ACT Academy, MNT Jaipur. We also thanks to all the participants for their enthusiasm in joining this FDP program. So we also thanks to our Honorable Director, NIT Calicut, for his supporting in facilitating this FDP project. So once again, I thanks to particularly Professor Vineet sir and Menaka madam for giving this great opportunity. I hope this FDP actually, it will benefit for all the participants actually. So once again, welcome all the participants for this FDP program. Thank you, madam. Actually, thank you, sir.
Thank you, Periyasamy. Dr. Menka, it's better to wait for Virendra because then we'll all be introduced to him that way.
Yes. Okay, sir. So by the time, may I request Dr. Lindu Rajan to say a few words to encourage our participants. Dr. Lindu Rajan is from NIT Calicut. She is coordinating at their.
Yeah. Thank you, Dr. Menaka. Good morning, all. So we are really happy to collaborate with Electronics and ICT Academy and MNIT Jaipur for conducting this FDP, that is VLSI testing and testability. So, and also we are thankful to Dr. Menga and Vineet Saula sir and Perisamy sir, the SPOC coordinator in IT Calicut, for giving us this opportunity. So this will be a very relevant topic that is going to bridge the gap between this academic research and this industry application. So all the best wishes to all the participants. Thank you.
Thank you, Dr. Lindu Rajan. So now I request participants to wait for 2-3 minutes. There is some issue with the joining link. Professor Virendra Singh is going to join us soon. So I'm trying to sort out this issue as soon as possible. Please wait for 5 minutes.
Yeah, till then, let us go through what AICT has proposed for all the institutes all over India. I will just have a short 3-4 slides matter presentation before you. Before I start, I think Dr. Nanda would like to say something.
Thank you, Dr. Nanda, for joining us. So may I request say you few words regarding this FDP, sir?
Voice nahi aa raha, Nanda ji.
Yeah, your voice is not audible, sir. Dr. Nanda.
No, I think up mic select karna. On the settings, you can select the mic.
Yeah, just a minute.
Now you're audible.
Okay. So,
Please go ahead.
Yes, sir, it's audible now. Yes, sir.
So I welcome all the participants to this very important course on VLSI testing and testability. And I am very happy that in this particular course, eminent pillars of VLSI in India, like Dr. C.P. Ravi Kumar sir and Professor Birendra Singh sir, they all are speaking in this particular FDP. So it will be eminent beneficial for all the participants to listen to them and learn the fundamentals of the VLSI from them. From Electronics and ICT Academy, MNIT Jaipur, under the guidance of Professor Binit Sahula sir, we are continuously organizing FTPs in the leading areas. And this particular program is one of them. In this particular program, I request all the participants to take full benefit of it and attend the most of the session as much as possible and give the quizzes in time so that it will be helpful for us to do the evaluation and give the certification in right time to all the participants. So there will be 2 quizzes and they are pretty means if somebody is continuously attending, there will be no problem in appearing them, and then all your materials will be also shared in the Canvas platform. And I wish all the best to the participants so that they can able to have a successful learning, and this certification will help them in shaping their future. Thank you.
Thank you so much, Professor Nanda, for your encouraging words to the participants. And we are having some Professor Virendra Singh is having some technical issue, so he is going to join us soon. By that time, I would request Professor Sahula if he is having something more to encourage our participants.
Yeah, I just have one thing to let them know that there is a scheme of AICTE by which any institute in India can start a minor major offering 5 to 6 courses along with the normal BTech program. So they can think of offering honor or minor in the field of VLSI design by incorporating about 5 to 6 courses of VLSI. We have this program is I think third or fourth in the series offered by us, where if a faculty member is following this, they will be quite exposed to the domain very well. So there is an offer from us also that any faculty colleague who is completing 5 courses from this domain, VLSI domain, maybe from any subtopic, spanning from packaging, fabrication, devices, circuits, system design, testing, verification, formal verification, and many more. So they will be additionally be awarded the PG certification after completing 5 courses. I have this something in a formal way on my slides about what IICT says and what we are offering. So if you just give me a chance to present that, I would like to.
Yes, sir, please proceed, sir.
So this program is about testing of VLSI circuits, and we have today's inaugural speaker, Professor Birendra Singh, IIT Bombay, and the coordinator is Dr. Menka Yadav from our department. She's my colleague there. VLSI testing is all about verifying after fabrication whether a circuit which has been fabricated is functionally correct and timing wise correct. There are no faults. Faults in the sense it could be a wire shortage or opening of wire or some signals not at all being processed and the output is not correct or not desirable in the sequence as well as in the value. So that is called the manufacturing test. which is VLSI testing and testability, which is a domain today. Now the point is, if we have a chip which has about millions of gates, 1 million means about 10 lakhs gates minimum, normal circuits which we now use. SOC have much larger amount of number of gates. And they're all sequential circuits in general. That way.
Hello.
Verifying. Yeah.
Sorry, time, sir.
Yeah. So to test such a circuit, suppose you have a PCB which has some 100 components, but because PCB is open to you in a way that its surface is open to you, you can put your probe anywhere, across any two devices, across any device on 2 terminals, or 3 terminals, or multiple terminals, whatever. But for a fabricated chip, which is a die, it is very difficult and impossible to probe any points in between. That's a problem. What people do during design time, we put some pre-planned probes. They are not just probes. They are just test points, test access points. They are called TAP, test access points, during design phase itself, so that the testing circuits which is on the chip is being designed along with the desired circuit and is being fabricated along with that circuit. And that is called design for test. And we have that chip much better testable. So this is the purview of this whole program, to expose you to that. Preliminary requirement is only just digital design, very well studied for combination and sequential design, some kind of exposure to algorithms, and of course programming, one of the language, anyway, whatever you prefer. So what I am going to let you know is what AICT offers that way. This is the list of our speakers whole throughout. Dr. C.P. Ravi Kumar has been in academia for at least 12 to 13 years in IIT Delhi. Then he joined Texas Instruments, and he has been there for more than 20 years, and so on and so forth. And Professor Viren Singh is also having an experience of more than 25 years in ISC Bombay, at IIT Bangalore, IIT Bombay, ISC Bangalore, and so on and so forth. Mr. Deepak Agarwal, Mr. Surendra Tadi, Tarun, Prateek, Harsh Sahai, they're all from industry. And we'll have, we are supposed to actually look at them very keenly to listen to them and go ahead with that. So the program, this is on behalf of Menka. I'm just letting you know. She will discuss more of it in her discourse, telling you what the schedule is. We have about 7 days, 6 to 7 days. Each day we have 5 hours, 9 to 12, and with a break for your working, and we'll resume in the evening from 6 to 8. Please remember that minimum attendance, some criteria is there for checking that. Please be there, log into WebEx. We automatically log in, your attendance is automatically logged in on the WebEx. There will be quizzes and assignments to be taken at Canvas. So all of you who have not joined the Canvas, please join it. The invitation has come into your email inbox or maybe spam, right? And if you don't find it, you can search your email that way. I'm sorry.
Sir, Professor Virendra Singh from IIT Bombay has joined with us.
Yeah, we'll just cut short.
Yes, sir.
So what I'm saying is the domain which I'm sorry, I'm trying to write. The domain is in structure.com. So you can search for this domain in your email and pick that email which is an invitation to join Canvas. Right. So this is joining by invitation only. All of you please join quickly. I will just quickly go through because our first speaker, Professor Viren Singh, has joined. So AICTE has actually approved the list of fields where honors and minors could be offered by any institute along India with no approval of AICTE. The only approval you may require at your institute is from your board of studies or any body you are following, that way, university or something. So these are letters from AICTE. I will discuss one of them. That is from Chairman Professor Sitaraman Sahab. He says what are the different fields where you can, they are indicative, you can pick and choose yours also, where you can offer the minor in any BTech degree, EC, electrical or computers. Just offer 6 courses that way. Even they could be from MOOC also for the students. So he says that at least 18 to 20 credits should be offered to a student that way. And to be able to offer that, a institute should have the faculty capable of teaching that. And because there is a shortage of faculty in every institute, what they say is a faculty from core area can teach these specialized courses if they have gone through at least 10 credits online through MOOCs in that field from SWAYAM NPTEL or other GOE portal. Our AICTE Academy is funded by Ministry of Electronics, so we are counted as a GOE portal. So if you follow our own course, possibly you will be capable of offering that. And 10 credits means about 4 courses, and we are taking care of that in the form of giving you a PG certificate for that field, let us say for VLSI design. So this is the list of VLSI design courses offered by AICTE, which span from material device circuits, system design, analog, synthesis, testing, embedded systems, and something on the equipments for manufacturing, reliability and yield engineering, which is very specific. And we are thinking in very next future we could offer to that. And these are the list of programs being offered by us. This has already been completed, right? These 3 courses have already been completed. This is 4th in the series, right? And this might be offering in the December again. So 5 courses have already been offered. You can look for our template for 2025-26, and we might offer these programs again live for that part. So this is all I can indicate to you. If you follow this and follow such 5 programs, you will be offered additionally a PG certificate from our academy or from any other academy you are registered at, right? So this is all I have to let you know. Let's welcome Professor Viren Singh, and thanks a lot to him for agreeing to support our program. He's an exponent in VLSI testing domain. He happens to we remember him very proudly as our alumni. Then he has taken up a job at CD Plani. He has completed his PhD from I think Japan or US with one of the supervisors from US. Having done that with accomplishment, he joined ISC Bangalore, remained there for more than 5 years, and now he is a professor at IIT Bombay, a accomplished researcher and a core academician who is interested in the pedagogy and teaching that way. So we are very glad and privileged to have him here. I will request Dr. Viren to have some 2-3 minutes address to the participant before we start his discourse today. Professor Viren Singh, please.
Hello, good morning. Am I audible?
Very well.
Yes,
Please go ahead.
So, sir, thank you very much for your nice introduction. I'm highly obliged to be the part of this FDP being a part of MNIT family. I started my career, my study from MNIT, and I spent good amount of time in MNIT since 1990. So I have very long association. Thank you very much for inviting me for this. This is a great opportunity. Uh, so in this course, as sir already mentioned, that we will be discussing about what is VLSI testing and why it is so important from the industry point of view as well as from the academic point of view, because we have two different dimensions to look at the problems, how industry looks at it and how academia looks at it. So we'll cover all the dimensions of this course. Maybe today we'll start with the very basics of VLSI testing, but then we will go gradually go for the advanced topics. I have been teaching this VLSI testing for last many years, and will try to say aware you about what are the research opportunities wherein the students, master's students or PhD students can take up the research topic so that they can contribute to this field of research. So once again, I would like to thank Saula sir and the MNIT for inviting me for as a resource person for this workshop. I hope this would be a fruitful exercise. Those who are attending perhaps may be able to offer the VLSI test program in their curriculum. Unfortunately, there are only a few groups who are working in this area in this country, whereas there is a huge demand in the industry. And whenever I'm talking to the industry people, they always complain that we don't find good VLSI test engineers who have this, some reasonably good idea about the VLSI testing. So perhaps I mean, it will help you in offering the courses for your students. So thank you very much.
Thank you, sir, for joining and accepting the invitation from our FDP to be the one of the resource person. Thank you so much. And now we are going to start our first talk. So I think all the panelists and the coordinators from the different institute to joining and making this course much more exciting by encouraging their participants. And Professor Vinit Sahula, Dr. Nanda from MNIT Jaipur, Dr. Lintu Rajan, Dr. Pariya Sami. I thank you so much for making it much more exciting for the participants and saying the encouraging words to us.
Dr. Menka, I will just interrupt and read a formal introduction to Viren so that participant can actually follow his research also.
Yes, sir. Yes.
So Dr. Viren, I'm just sharing participant his link where we can actually appreciate the way he is, and you can contact him also later. There is a short bio I could access from him. I'm sorry if I'm missing something from that Dr. Viren. Dr. Viren Singh, he is a senior member of IEEE, received B and me in Electronics and Communication from MNIT in Jaipur in 1994, 96, and a PhD degree in Computer Science and Engineering from Nara Institute of Science and Technology, NIST, Nara, Japan in 2005. He has been with Siri Flani for long. He is currently a professor with IIT Bombay, and prior to IIT Bombay, he was faculty member at SERC, Supercomputer Education Research Center, Indian Institute of Science, Bangalore, from 2007 to 2011. His research interests include high-performance computer architecture, testing verification, high-performance processors, student computing, design for test, formal verification of hardware designs, embedded system design, design for reliability, CAD of VLSI. He is also member of ACM and VLSI Society of India and life member of IETE. If I have missed something, I apologize, Viren. Please, the stage is yours. Please go ahead. Thank you.
By that time, may I request Dr. Bindia TS from NIT Calicut to say a few words regarding our FDP to encourage our participants.
Hello, hello, am I audible? Hello.
Yes, madam.
Yeah. Thank you, MNIT Jaipur, the administration of MNIT Jaipur, and thank you, Vin Chahla sir, for this opportunity to join this FDP. And to the participants, so this VLSI testing, the topic VLSI testing and testability is a very advanced topic in the field of VLSI domain. Even though the verification is very, VLSI verification is very popular. Testing is also is a very important topic, which cannot be avoided in the when we fabricated IC. So I hope this course will be advantageous to all. And I hope all the participants will make a good use of this. All the best for all the participants. Thank you.
Thank you, Dr. Bindia. Now we have the expert lecture from Professor Virendra Singh. Professor Virendra Singh, it is over to you, sir. Thank you, sir. Professor Virendra Singh, am I audible to you?
He's just setting his presentation.
Hello.
Yes, sir. We can hear you, and we can also see your screen, sir. You may proceed, sir.
Yeah. Now is it full screen?
Yes,
Yeah,
sir.
Viren,
Full
please
screen,
go
sir.
ahead.
Thank you so much. Yeah.
Okay. So thank you. I'm sorry, extremely sorry for this all delay created because of getting access to this WebEx. I'm maybe we can quickly start. Sir, how much time we have?
Viren, up to you. We have about 2 hours. You can take
About 2 hours. Okay.
at your convenience, not a problem.
Okay, thank you.
Yes.
So, as I mentioned earlier, that we are going to cover in this lecture what is VLSI test, how it is important, and where we can what are the say benefits of studying this particular course. I acknowledge the contribution of various people who helped me in preparing this presentation. First, Professor Hideo Fujiwara, who was my PhD advisor almost 2 decades ago. Professor Keval Saluja, who was my co-PhD advisor, and my other collaborators, Professor Fujita, Professor Adit Singh, Professor Vishwani Agarwal, and then my research was supported by Department of Science and Technology and Japan Science and Technology Department. So here in IIT Bombay, we have a reasonably large group of people who are working with us in say various fields. We have a group called cyber security, cyber physical cognitive systems, compilers and processors, wherein the aim is to make a secure and smart world. So we have a lab called computer architecture and dependable systems, wherein we are largely working on the dependable systems. Dependable systems mean the systems on which one can rely upon. this is a photograph when our Japanese collaborators visited us, and we had a internal workshop here in IIT Bombay. We have various projects in which we are involved on security, on cyber physical cognitive systems, and security of AI kind of systems. We have done a whole lot of things. Now maybe I start my lecture on set of the education and how VLSI test is coming in this ladder, wherein it's worth to give say a few seconds to look at the aim of education, why one should study. So in terms of or in the words of Ravinathji, education means enabling the mind to find out the ultimate truth, which emancipates us from the bondage of dust and gives us wealth, not of things but inner light, not of power but of love. It is a process of enlightenment. That's very important. It's a divine wealth. It helps realization of truth. So what it say creates us, or so it develops us intellectually. That means the development of our imagination, a creative free thinking, curiosity, and alertness of our mind. Now these are the aims of education. That means here the aim is to make a person good human being. Now so the very first thing is one must be good human being. Then in here in technical education we are studying engineering. Now if you look at the engineering, what engineering means? Engineering says a profession in which the knowledge of mathematical and natural sciences gained by study, experience, and practices, which are applied with judgment, very important point, are applied with judgment to develop ways to utilize economically the materials and forces nature for the benefit of mankind. I believe this should have been a living being. So that this says that it is a profession that uses the knowledge that we acquire from natural science and mathematics that can help us in changing or modifying the nature. So we in science we study how the nature works. In engineering we modify the nature, but when we modify the nature we have to apply our judgment which way I should modify the nature. For example, we know that the nuclear energy can be used as a power source, and we can build a nuclear reactor and power up the industries. However, the similar concept was used to build a nuclear bomb and then destroyed two beautiful cities in Japan, Hiroshima and Nagasaki. So now here this is where the judgment comes, that what I should build and what I should not build. That is the task of an engineer, and therefore one must be say a good human being, so that he or she can apply this process with the judgment that what technology I should develop, what I should not develop. Now say so in engineering, if we look at engineering, is all about the how to solve the problems that human is facing. So the initial requirement were the shelters. People were building the houses like this one. Now and now time has changed. Over the years we have developed the better engineering techniques and building say very fancy buildings. Another requirement was mobility of people from one place to another place, and the very primitive solutions people were using, like using only wheel, you can transport some people from one place to another place. Now we have created cars. Then communication was a third requirement, wherein people were using birds and etc. to communicate from one place to another place. However, we have developed a fancy technology wherein a person sitting on camelback in very remote area of Rajasthan can talk anywhere at any point in time. So that's kind of things that we have developed now. What next? That is the question. All these technological development has helped say in big way to the humanity that or the evolution of society or civilizations. Initially, maybe many years ago, human were like keep on roaming around, just like gathering the food and eating. Then almost like 15,000-16,000 years ago, we started to, we learned how to grow the food grains, and then we started to settle close to river banks, and we transformed our society into a agrarian society that we call as society 2.0. Then nothing had happened for say 15,000 years. Then in 17th century or 18th century, with the development of loco, again there was another transformation or evolution of society, wherein we started to develop say industries, and then the urbanization started. The society was like a revolve all around the industries, and therefore we become the industrial society, and we call that as a society 3.0. Then as time progressed, there was a rapid development in technology, and in last century, with the invention of computers, followed by the internet technology, again our society has been evolved to society 4.0, or we call as information society, whereas the information was the backbone of the society. And now we are heading to the newer avatar of this or transformation of the society that we call as society 5.0 or super smart society. What relationship this has with the VLSI testing, I'm coming to that point. So in all these societal evolution was always backed up by the industrial revolution. It started from the first industrial revolution, wherein we developed the light industry, followed by the second industrial revolution, wherein we had heavy and chemical industry, and third industrial revolution, wherein we developed computer and internet. Though computers were, there were many efforts to develop the computers in early 20th century. Even at that time, IRE, the Institute of Radio Engineers, and American Society of Electrical Engineers, they set up differently some committee to start some kind of work in the area of development of computers. But the main thrust came during the Second World War, wherein there were maybe majorly the two requirements, wherein people felt that we need a heavy computing device. One was the breaking the code that Germans were using in their Enigma machines, and another one was the printing the tables for the trajectories of the cannons that they were firing, because cannons can go fire a bomb that can reach to something like a 20-25 miles, and the trajectory is influenced by or deflected by the wind velocity, and therefore you need to develop some tables for that. So computer was developed for these. The big thrust came during the Second World War to develop the computers, because of these reasons. Fortunately, unfortunately, none of the computer system was developed during the Second World War. All initiatives concluded just after the World War was over. So that was the third industrial revolution. And now in order to say make or to make society 5.0 as a reality, we have the fourth revolution, industrial revolution, that is dependent on digital transformation, artificial intelligence, IoT, blockchain, etc., etc. So now in so if I look at this, the one a major component in this one is a cyber physical systems, wherein there are physical systems which are controlled by the cyber system. Cyber system means it can be electronically controlled or it can be controlled by software, so which you can run on a processor. For example, you can have the say autonomous vehicle, you can see drones, you can see a pacemaker. All these are the cyber physical systems. That is the society 5.0 through industry 4.0. Now we are moving to the next phase of industrial revolution, and that is we call as industry 5.0, which is really the maybe the key theme behind the society 5.0. So in society 4.0, the main focus was the automation. That means you have to move human out of the loop. Everything has to be done by the machine, and therefore the main focus was on generalization of the things. However, in industry 5.0, we take a or we took a step back and look at that, really do I need to move the human totally out of the loop and let everything be done by the machines? And the answer was no. I mean, human has natural intelligence. The machines started to acquire the intelligence, and now why they can't work synergistically? So therefore the human can give some kind of vague clue to the machine, and machine can refine and can work. So therefore the main focus went to the customization of the machines, so mass customization, as well as the cyber physical systems which we were using became the cyber physical cognitive systems, because they got the cognitive ability. So now it is the synergistic work of the society, I mean human and machine. So industry 5.0 priority is to utilize efficiently the machine and human synergistically. This makes a significant change in the industry 4.0 and create a smart factory, or which is by and large based on the Internet of Things. Now perhaps you might might be hearing this word Internet of Things for a long time. So what is the thing in Internet of Things? Thing is a machine that or a system that can compute and communicate, but should not be a computer. That can be your phone, that can be smartwatch, can be smart ring, TV, car, etc., etc. So it has four components. It can sense the environment, can communicate, can do the computation, and then can modify the environment. So that means there can be a actuation, and this all will make a this world as a smart world. So now a smart world is the key theme behind smart society. In a smart world, we can have a smart city. Within the smart city, we can have smart education system, a smart transportation system, a smart energy system, and so on and so forth. So that means here there are multiple systems which are working in coordination with each other. So that means that the coordination is the key behind this. Like for example, within that I can have a smart home. In a smart home, when you enter into the home, it has to recognize you, automatically open the door. When you go and sit, it has to identify that what is your mood, and then start to play the song, or start news, or something like that. The air conditioner system will also start to focus towards you, so should not be like here the work on cooling the entire area in equal fashion. So all those kind of things you can, I mean, it has to do. when you go out, it has to open the garage automatically, bring out the car, and then you can sit into the car and then can order. So now this is the smart transport is another transportation is the another industry which has been totally transformed over the years. Couple of decades ago it was only the mechanical engineering industry, but now it has become totally transformed and became the industry of electrical engineering or computer science. So there's a huge transformation that has happened, wherein you sit in a car, just order where to go, and then you can do your own job. It can identify which path is the shortest path, and can take you navigate through that, and take you to your destination. So like that, here there are numerous examples. The smart farming is the another thing, wherein rather than having the horizontal farming, you can do a vertical farming, and can have the more controlled environment. That controlled environment can produce better say vegetables or food grain, or whatever you are growing. So this is again the game changer, which is changing the totally the agriculture sector. So like this, here there are numerous examples, and all these things will come with some cost. So now if you look at the growth of IoT, in that case, over the years, now here at around this time, maybe we have close to 330 billion IoT devices, which is like here many times more than the population that we have on this mother earth. Even we have more than 10 billion computing devices, which are like here again more than a device per person in the world. So this is the kind of growth we are going to have over the years. Now look at that. So in this one, there are various kind of systems. One of the system, maybe you can see as a say a mid-size sedan car, which has whole lot of systems. Some system is responsible to control the braking, some system is responsible to inject the fuel, some system is responsible to keep the stability of the vehicle, and so on and so forth. So now so this becomes like a kind of system of systems. So if you look at any say even not autonomous, but any mid-size sedan car, it runs, I mean, it consists of say 100 to 200 compute processor cores, and a humongous software running on top of that. Maybe a mid-size sedan car runs about 1 billion line of code. That's the kind of program we are running on these kind of machines. So now every system is a big computing system. That's the kind of thing that we have. On top of that, we got now the big boom of artificial intelligence, wherein systems want to learn from the environment. The AI is as old as the computer system is. In 60s, people were expecting that in next 10 years, all the systems will be replaced by the artificial intelligence system. That had not happened. Then in another boom or wave came sometimes late 80s or early 90s, when I was BTech student. I mean, everybody was talking about the artificial intelligence. There were many expert systems were developed around that time, but then by the end of 90s, that boom had gone. Then again, now it has come up as a the third wave in artificial intelligence, which is based on the statistics, which became the big success. And this became big success because of three things. One is today we have availability of the compute power, and that compute power is not available to only to the big industry or the universities. This is also available to any individual. You can rent it from any cloud, pay as per use. So that means here it is accessible to every individual. The second thing is, now so many platforms were created, so you even don't need to write even a small piece of code. You can just integrate the various software or platforms which are available, and then can run your programs. And third one is the humongous amount of data is being generated through these IoT devices. So all these things were not available in earlier two waves, which are available now, and that can help you in doing much better than the earlier waves, and this became a big successful wave. So in all these, in AI became successful because we have humongous compute power available to us today. Now all these things are have one thing which is very essential part, which is the compute power. You have a computation facility available. Because of that, all these things are happening today. Whatever the devices that you are looking around you, which is we call as electronic device, have a at least one processor and some digital logic around it. Now and this history is not new. Maybe as I discussed earlier, in 30s or 40s, people have developed multiple computer systems which were not like today's system. Like this is one system that was developed in University of Pennsylvania by Professor John Mockley and his student Presper Eckert. And you can see that the system was very large system. You need a large room to even house this system. It used to consume humongous amount of power. You cannot imagine that the power consumed by this was 130 140 kilowatts, not the watts. And that time there was a scarcity of power, and once if you want to power on the system, you have to power down the city. So that was the time. Over the years, there was a huge development. This view graph shows that the how a single chip computer had been evolved. So the first single chip computer was developed by Intel. That was 4004, which was essentially say calculator chip, which could do 4 calculation tasks: addition, subtraction, multiplication, and division, which was the requirement of a Japanese company who wanted to develop the electronic calculator, which became very common across the world. Like every shop used to have a electronic calculator. Now perhaps that has gone out. But maybe until few years ago, you could see everywhere there's the electronic calculator. So they started their journey from 4004, which was implemented using about 2000 transistors. And now we are in the era wherein you have multiple cores, and then we are fabricating something like several billion transistors on a single chip. And this humongous growth of ICs is coming with a whole lot of advantages as well as the challenges. So you can see that here the number of transistors or transistor count had been grown tremendously over the years. That's the exponential growth. No other industry has seen such kind of growth. That's the amazing. So Now, but now everything is has not gone that well. This is one famous quote from Robert Kringley. He says that if automobile had followed the same path or same development cycle as computer, then a Rolls Royce today would have costed about $100. So you could buy a Rolls Royce in $100, get 1,000,000 miles per gallon. However, it can explode once a year and then kills everybody who is inside that. So today we are in that era wherein we are getting humongous compute power, so very high performance. Uh, However, this comes with the on the cost of reliability. We cannot rely on our device whether this device will work or this device won't work. You might have seen so many times that your devices, whatever you are using, are hanging on and off, right? So you are doing very important work, and in between your mobile hangs, and then you have no other choice other than rebooting that. So we do we want that kind of system? Perhaps not. We want these systems as reliable as the say Rolls-Royce car is, or some any other automobile is. So that's what perhaps is the theme of this particular FDP, that how we can make our systems reliable. So now if I look at the development process of any digital system or VLSI systems, it starts from the customer's need and goes all the way to deliver a chip to the customer. Now, during this process, what we do, customer comes with a need, can tell you that here what I want, but they can only tell you in the spoken language that if I'm developing a microwave oven, I need a microwave oven controller, and how microwave oven controller works, that if I put rice in that, then it should operate at 300 watts for 10 minutes. If I put milk in that case, it should operate at 200 watts for 8 minutes, and so on and so forth. Those are the kind of requirement customers comes with. Then the engineer has to interact with the customer and can figure out that do I have the full requirement for the system or not. If you do not have, in that case you have to interrogate again the customer and make the complete set. Interrogation means you say that here, oh, what happens if this condition arise? Then maybe customer may say that here, yeah, I mean, you have to do this thing if this condition arise, or maybe customer can say that here, I don't care about that. If that condition arise, this can do anything, or can say that here this condition will never ever arise in my system. Like for example, if somebody wants to make a memory controller, and then can provide you two interfaces, one is memory read and one is memory write, and then can say that here either I would be reading that memory or I would be writing to that memory. The both read and write won't happen simultaneously. So that kind of things maybe customer can tell you. Then we have to, from this requirement which is there in the natural languages, we have to write in a very say formal way, that we call as the specification of the system, that we derive out of this customer's requirement. And this should be formal. So ideally this should have been mathematical way of representation, which perhaps is bit painful to write. So I'm not going into that detail. Maybe later we will discuss something about that. But we are generally writing the specification in terms of hardware description language, which are not a formal languages, but they are like a semi-formal kind of languages, wherein formal, I mean that here those are totally unambiguous. Like if you write something in mathematical way or mathematical expression, in that case that is unambiguous. Whether you read that or I read that, all both of us will understand the same thing. However, if you are if it is a natural language, in that case that is context dependent, and you may infer something out of it, I may infer something different out of it, so they are ambiguous. So natural languages are ambiguous, mathematics is unambiguous, and HDLs are in between. They are by and large unambiguous, but then there is some ambiguity still exists in those languages. But therefore in most of the languages like that we are using, whether VSDL, Verilog, System C, or any other language, the entire set of that language is not synthesizable. You can only synthesize a subset of that. Now, once I write the specification, in that case we go for the for designing the circuit. And the designing circuit means here you have to go through some transformation. So something is written in RTL at high level abstraction, and you have to generate the gate level netlist or transistor level netlist. And to generate that, we have to go through several transformation, and those transformations are mathematically correct. So it has, you have to carry this through the transformation. Let's say, for example, I tell that if there is a Boolean expression, you can use K-map to say minimize that. Now the expression that is given to you and an expression that you are getting after K-map minimization is exactly the same function that we have. And so that through K-map we are doing the transformation from one representation to the another representation, and then now another representation that we are getting perhaps may be more economical, and we can synthesize that. Now so all the transformations that we are using are mathematically correct, but still we need to verify each and every design. So that means we have to verify whether after every transformation my design is correct or not, vis-a-vis the given specifications that we have. So now the question comes that why I need to verify when all the transformations that we are using are say correct, mathematically correct. There should not be any requirement of verification. I just go through the transformation, and then after transformation whatever I am getting, I can easily assume that it is equivalent to the specification and then can fabricate that. However, at every stage we need to verify, and that comes with humongous cost. Maybe 50, 40, 50, I mean 50, 60% cost goes to the verification only. So that's the very painful job that we have. Now, why do I need to verify every design? Because though the transformation that we are using are correct, but these transformations are implemented using a program. Now, there is no guarantee that program that you are using is correct, and thereby so either if I can say that the program that I'm using is correct, in that case I don't need to do any verification, and the total verification phase is gone out. However, verification of program is much harder problem than the verification of a hardware design, and there is no system which is completely or no big software which is completely formally verified, and therefore we cannot take a chance, and henceforth we have to verify after each and every transformation step. That comes with the big overhead. Now once I verify my design and develop I have transistor level netlist, from the transistor level net list, I will do the placement and routing, and then after routing we develop the GDS2 file that we send to the fabrication house. Now fabrication house will fabricate that chip, and then every fabricated chip has to be tested, because while you are fabricating, something can go wrong, and if something can go wrong, in that case I have to make sure that the fabricated device is good device. So every device has to be tested. Now when I test, some device may be good, some device may be bad. If there is a good device, in that case I will ship that to the customer. If it is a bad device, in that case just I will scrap those devices. Now to apply, I'll discuss in a minute that how difficult this test process is, and that is the theme of this total course. So we need to develop a stimuli or test vectors which we can use to test that particular chip. So so then there is another phase that we have to have, that can develop the test vectors which can be used to test that particular chip, and what is the test vector and all those things, like we will discuss in due course of time. So now here I have used three different things I can maybe formally define. One is the design synthesis. Design synthesis means a given an input-output function, develop a procedure to manufacture a device using the non-material and non-processes. So I mean, I have materials, I have non-processes, and then can implement. If I look at the digital design, in that case, what I need a set of switches to implement that. Like using a set of switches, we can implement any gate. Like for example, if you have two switches, one is maybe PMOS, another is NMOS. In that case, you can design an inverter. In the similar way, you can design NAND gate or NOR gate, AND gate, OR gate, something like that. So you need a couple of switches. So using those switches, you can synthesize the system that can provide you a given input-output functionality. Another thing that term that we were using is verification. Verification tells about the predictive analysis of the design to ensure that the synthesized design, when it will be manufactured, will perform the given input output function. So that means here my design means the configuration of the switches that we are using is such that when you manufacture those, it will provide you a given input output functionality. And third term that we are using, test. Test means a manufacturing step that ensure that a physical device manufactured from the synthesized design. So I have a synthesized design and then a manufacturing process. If I manufacture from that using that process, in that case it has no manufacturing defect. Now maybe quickly I can tell here is that what can be the manufacturing defect. Say for example, I want to connect two gates, and to connect two gates, what I need a wire, and wire is a metal connector that I use between the 2 points. Now when I draw that metal wire on silicon, what can happen is that say if there is a dust particle sitting over there, in that case that wire may not be say routed on top of that dust particle, and that due to dust particle you may get a break between the two end of the wire, and hence your circuit may not work. So at some point in time you may get a dust particle, some other point in time you may not get, and so some devices may be defective, some devices may not be the defective. So the test is again I reiterate, is a manufacturing step that ensure that the physical device, when you you manufacture from a synthesized design, won't have any manufacturing defect. if you look at the conventional SoC design flow that we are using today, is like here we are not writing the manual RTL. What do we do is we have a high level program. Say for example, I want to develop a video decoder. As let's say that here S dot 264. So if I develop a video decoder, I have a program for video decoder in C or C++ or high level language. Now, rather than writing a RTL manually, what we can do is we can go through the high level synthesis, wherein it takes the program as input and emit the RTL, which is automatically generated by the machine. Now, when and after generation of the RTL, you can go through the same process that we have discussed so far. You go through the logic synthesis, placement routing, verification of that, and then say develop the test set and then send to the fab, and then from fab you get the chip back, which are good. Now when it is generating the RTL from a high level code, what it can, I mean, it may have some bug. That means here the somewhere it may not have understood your high level description correctly, and then may have introduced some say bug, and therefore we have to look at the or go through the verification of that code, that whether this particular generated RTL is adhering to the specification that we have. And what specification we have? We have high level code. High level code can be represented using the data flow graph or control data flow graph, wherein you have control structure as well as the data flow structure. So now we have to check against that. Either it says that here it always adhering to that. If it doesn't adhere, if there is a bug, in that case you have to find out that in the entire code where is the bug. Fortunately here it is a simple piece of code which is written in different language, maybe in VSDL, Verilog, System C, or some such kind of languages. Therefore you can probe any signal and then you can localize the bug. If you localize the bug, in that case you can fix that bug, that oh, maybe it may possible that the OR operation has been, I mean XOR operation has been replaced by OR or something like that, and then you can fix, and then now again check whether it has any other bug or not. So that we call as pre-silicon verification. Once I get the chip back, in that case my manufactured chip again has to go through the validation phase. So the chip which I test and passes the test, and then we have to see whether I mean it adhere to the specification or not. That we call as post silicon validation. Now in post silicon validation, the big issue is that when I have a chip, only I can visualize, I can say probe the primary output. I cannot see the intermediate signals, which was the luxury I had in pre-silicon verification. I can probe any signal, whatever I want. Now I can see only the signal at the output. So for example, if some error is introduced in cycle X, maybe it may appear at the output of the system after 1 million cycle. Now it's a big humongous task to localize the bug, that where that bug had started, and then now what was that particular bug. And so if I can localize that, then I can fix that bug. But unfortunately now the chip has been fabricated. I cannot do any modification in chip. So again I have to develop the new RTL after fixing that bug, and go through the entire synthesis process, and have to manufacture chips again. when you manufacture chips again, in that case it will cost you same amount again, because you have to change all the mask set that fabrication house is using. Now say if I use, say for example, 10 layer metal process, almost every layer mask cost you something about $1 million. So that means once if I fabricate a set of devices, it cost me $10 million, and then again if I go second time, in that case again $10 million. So this is quite expensive process, and we want to avoid this as much as possible, because it is too expensive. So whole lot of say effort goes in the post silicon validation. First, it's very difficult to isolate whether that the wrong output we are getting because the manufacturing defect, or because of the design bugs. That itself is a challenge, how to isolate whether it's a defect in the manufacturing process, or it is a bug that was there in the design. So I mean, this was the view graph bit older, but this says that here almost like a 50% time of any design process goes to the verification, and only 30% time goes to the design. And this was almost like a quarter century ago. Now what has happened is we have moved from the design from scratch to the IP based design, and therefore the effort and time required for the creation of design has been reduced dramatically. So this comes down to from 32% to maybe 20-25%, but the verification time has extended from 50% to 60-70%. So that's the kind of time consumption that we have in industry. So first let's look at quickly that here how difficult the verification process is. Maybe I will pick a very small example of a DVD player. I don't know whether you people have used that. Sorry, I picked up the wrong example. I mean, earlier during my time, everybody was using the DVD player. So let's say DVD player has 6 inputs. Now those are say play, pause, stop, for fast forward, rewind, and we don't press anything. These are the buttons or inputs that we can provide to that. There are 5 internal states. One can be the system is in the stopped state, can be in pause state, can be at the playing at normal speed, or fast forward at 2x speed, or rewind at 2x speed. So these are the five states, and you can make a state machine like this. Very small state machine has five. Hello.
Yes, sir. We can have a 5 minutes break, and after that we may continue.
Give me 2 minutes. I will complete this example.
Okay, sir. After that, we will have a break of 5 minutes
Sure.
or 10 minutes. Up to you, sir.
Sure.
Yes,
Yeah.
sir. Thank you.
So let me complete this example. So now this is a small state machine, or all of you must have designed these kind of state machines with 5 inputs, five states and 6 inputs. Now how difficult this exercise is. Now DVD player job is to play a movie and then show you on the display. Now let's say that here the display size is 1024 by 786. Now we have far larger size displays that we have. Every pixel is representing a true color, so that means here it uses 32 bits for that. Now by this, if I can say how many discrete states we can have on the display, the every pixel is represented by 32 bits, so therefore 2 raised to the power 32 states of 1 pixel, and then there are 1024 by 786 pixels. So 2 raised to the power 32 raised to the power 1024 into 786. And then now we can go from one state to the next state. So that means from any state I can go to any other state that is there in the transition diagram, and hence the number of combinations from the current state to the next state would be just like from this many states that we have here to the same number of states, and therefore this would be squared. So now these are the total number of states we can have. If I mean I can little bit simplify this, that if the every pixel is independent, in that case you don't have 2 raised to the power 32 raised to the power 1024 into 786, but this would be 2 raised to the power 32 multiplied by 1024 multiplied by 786, because every pixel can be the independent. But then you have, so the total number of states that you can get is number of pixels that I can have multiplied by the possible colors that you have, and then the number of internal states that we have. So 1024 into 786 into every pixel can be represented with 32 bits, so 2 raised to the power 32 multiplied by 5. That is this big number that we are getting. Now if you say that the old transitions from current state to the another state are considered, in that case, because there are 6 inputs, so it can go to any other state giving the six inputs. So now you will get the total number of next state, that is equal to the number of pixels multiplied by number of possible colors and multiplied by the possible inputs. So this much number. Now possible current state to the possible next state that we need to verify is multiplication of these two numbers, and that number comes out to be a humongous 3.4 into 10 raised to the power 32. If I can assume my simulation engine can verify. So simulation engine frequency is something like a 1 vector per second to 10 vector per second or something like that. It's not, but I'm assuming that it can verify a million transition per second. That's unreasonable. But even if I use that, you can see that here we need several billion centuries to verify that design. A small 5-state machine needs this many years to verify that. That's the gravity of this particular problem. So this is a very serious problem. Now, until your design is completely verified, we don't have trust on that particular design. Now, how to work with that? There are primarily in industries using two ways, and now going towards the third way, which is the formal way. One is you simulate your design with a given inputs. Now the given inputs are very small, like you can see that a very large number of inputs I need to verify, but you can apply very small in number. So what we do is we have to look at some kind of corner cases, which are more interesting, and therefore now today industry says that earlier days industry was looking for the smart people who can quickly create new design. So that means mostly the VSDL Verilog coders. Now industry says that I need people who can envisage these kind of corner cases that may arise, because they are most important thing. People can create the design quickly, even if they are not very smart. They, as most of the time we are making a system using some pre-verified IP blocks. So but after that, when you integrate, you don't know that which interaction among the different modules can result into the incorrect output. So for that you need people who can say envisage the corner cases. But whatever you do, there is a possibility that you can miss some corner cases, and then the bug can slip through. If bug can slip through, in that case that may be identified somewhere. If it is identified somewhere, in that case you will get back the chip, and that chip that would be a quite expensive job. Another way is that you emulate the design. So that means you can implement your design on FPGA, which was the basic purpose of development of FPGA, that you can say put your entire design on FPGA and then try to apply as many inputs as possible. FPGA works much faster because it can work at several hundred megahertz. That means that it can apply far more test vectors in the same given amount of time. So but the problem here is that still now we are relying on the simulation pattern, which for that here we have to find out some corner cases and have to check for that, and we are again likely to miss some of the corner cases, though emulation can give us little bit better say confidence than the total simulation. The third one that I have not listed over here is the formal way of verification. So that means you can verify the designs mathematically. For mathematical verification, first of all, we have to write the specifications mathematically and then have to use that mathematical representation on the say given circuit, whether it's a combinational or sequential circuit, and then have to say verify that. But the unfortunately the capability of a still for formal verification methodology is very limited. You cannot handle very large design. Maybe we can handle up to 10,000 flip-flops design or so, whereas in practical systems today we have several million flip-flops. So you can see that the difference that we have. So now what industry is doing is we are doing the hybrid kind of verification, simulation plus the formal techniques. So these are the challenges that we have. Maybe we can take a break over here and then move to the next topic, that is the test. So once I have a specification, we have to verify the design. Once it is verified, in that case you send that to the fabrication house. Fabrication house will fabricate and then have to test each and every device. Now how difficult that process is, maybe let's discuss after the break. Maybe we can take 10 minutes
Yes, sir.
break and
Thank
we
you
can
so much, sir. Let us have a break of 10 minutes. After that, we'll join back.
Okay, thank you.
So we will join after 10 minutes.